Hi folks, so we're into kinematics. We're going to start this out in this differential calculus unit, but continue it after the holiday break. So a little bit of vocabulary before we get started. This document is also uploaded on our Google Classroom, so feel free to take some notes to the side. So kinematics is the study of motion. A lot of what we're going to be looking at for kinematics looks at particle motion, but it can go beyond that. So a path is a set of points along which an object being studied is going to travel. We're going to be using some of the things we've learned about calculus to help investigate the path of a lot of different objects. And then we have the distance traveled. So that is the total length traveled after leaving the starting position. It is important because this is a scalar quantity, meaning that it has magnitude, or it is a numerical value, but there isn't a positive or negative to indicate the direction. Okay, so distance is never going to be negative. It's just calculating the total length traveled. Then we have displacement. So displacement is the difference between where the object started and its final position. Okay, so it is a vector quantity, so there is magnitude and direction this time. So we're looking at the values could be positive or negative. I find the drawing down here very helpful for seeing the difference between distance traveled and displacement. And then we have ST. So this notation here is going to be important. We call this our position function. A lot of what we do will start with the position function and will give us some information about the velocity and acceleration from there. So a couple important pieces of information. If the position function is greater than 0, then the p-value that we are looking at is to the right of the origin. Okay. If the position function is less than 0, then the p-value we're looking at is to the left. If it's equal to 0, it is exactly at the origin. Again, as we do some problems, a lot of this will make more sense. So velocity, this we find by doing the derivative of the position function. Okay, so we have looked at average rates of change and instantaneous rates of change so far in this unit. And so we're looking at the average rate of change of a position over time. So this is typically denoted by v of t, or you can say the derivative of the position over time, or the derivative, or s prime of t. All of these are just different ways of telling us that we are looking at velocity. So velocity is a lot like speed. It's basically telling us the average distance over time, but there is a direction involved. So speed would normally be something like 72 kilometers an hour. Velocity would be something like 72 kilometers an hour east. So the directionality is important. And then acceleration is the derivative of velocity. So this is going to look at taking the derivative of our velocity function, and it's going to tell us our average acceleration over a period of time. So when we're looking at this, the change in velocity is really what's telling us about our acceleration. So it's telling us if things are speeding up or slowing down. This is denoted by AT, or the derivative of velocity over time, or v prime of t. Okay? As we go through these problems, we're going to look at different ways to interpret each function. A lot of it's going to come down to doing sign analysis, or inputting values into the velocity, acceleration, or position functions. Okay? So here's a little table that can give you just a brief piece of information about what the values that we are finding when we plug into the position function, into the velocity function, and into the acceleration function, and what that tells us about the movement. So for our position function, it's going to tell us the position in reference to the origin. Okay? The velocity function is going to tell us the speed. Okay, and the speed and the direction. So if it's to the right, if we're getting a positive, to the left, if we're getting a negative. And then acceleration is telling us if the velocity is increasing, speeding up, or is the velocity decreasing, slowing down. Okay. So speed is important. We're going to be looking at the speed of different objects. So what we need to know is what's written in particular in these 2 bullet points here. So if we discover that the signs of the velocity function and the acceleration function are the same when we do a sign analysis, so for example, both are positive or both are negative, then the speed of the object is increasing in that specific direction. Okay? If we discover that the signs of the velocity are different, so perhaps one is positive and one is negative, then the speed of the object is decreasing or it is slowing down. Okay. So let's get into our first example here. So it says a particle moves in a straight line with the position relative to O given by this function, where t is the time in seconds and t is greater than or equal to 0. As you're doing these problems, I would highly suggest have perhaps Desmo's graphing, make a graph of what is happening here so that as you're doing the problem, you can always verify that the things you are finding make sense given the position function originally. So the first says, find the equation for the particle's velocity and acceleration. So velocity is just the derivative of position. So like what we were doing in optimization and when we were doing graphical analysis, we're going to take the derivative of s of t. We typically write this as v of t. So we'll get 3t squared minus 3. And then to find the acceleration function, we take the derivative or take the second derivative of the position function. So this would leave us with 6t. Okay. It does say in the question it also wants to draw a sign diagram for each. So we need to figure out when are these equal to 0 and then do a sign analysis. So for the velocity function, I would end up with a 3 is equal to 3t squared, or 1 is equal to t squared, and I'm generating a positive or negative 1, but we can't have a negative 1 because of the domain restriction given in the question, so we'll just do our sign analysis around positive 1. Okay. For this one, the only value that makes this true is if t is 0. So we will test around 0 into the acceleration function. When you do this, what you're going to discover is that a value to the left of 1, so somewhere between 0 and 1, because it does need to be above 0, is going to give us a negative. Okay? And then above is going to give us a positive. In the acceleration function, well, this region does not exist in the domain, so I'm not even going to do a sign analysis there. I'm only going to do it above 0, and I would get a positive if I were to input a positive number into the acceleration function. Okay, so the next question says, can you find the initial conditions and describe the motion at this instant? So this is saying what's happening when t is equal to 0, right here. So let's plug t is equal to 0 into our position function. When we do this, we're left with just 1. When we plug 0 into the velocity function, we're left with negative 3. And when we plug 0 into the acceleration function, we end up with 0. So again, I'm just plugging it into these functions that we found in A. So what does that tell us? So this is when you would go back to this table to use this information to be able to interpret. So when in the initial position function, the 1 is saying that the particle is 1 centimeter to the right of the origin. Where we're getting negative 3, that's telling us about the particle's movement. So this is saying the particle is moving to the left with a velocity of negative 3 centimeters per second. Okay. And again, I know this is in seconds because it was provided in the question. Time is in seconds. Okay, and A being 0 just means that our velocity is constant. So now let's go down to C. So it's just expanding a little bit farther. It's saying describe the motion, but now at 2 seconds. So when we reach this position here, what is happening? So again, let's plug a 2 in. When you plug a 2 into the original function, you would get 3. Okay? When you plug a 2 into the velocity function, you're going to end up with a 9. And when you plug a 2 into the acceleration function, you're going to end up with a 12. So now we can do a little bit of analysis again. So the first position function is telling us that the particle is 3 centimeters to the right of the origin. Okay. The second is telling us that this particle is moving to the right with a velocity of 9 centimeters per second. And then the 12 is telling us, and when I'm looking at this 12, I'm looking at the fact that I'm seeing a positive here, and there's also a positive in terms of the velocity. So if you remember about the idea of speeding up or slowing down, speeding up are when we see that both the velocity and acceleration functions have the same sign. So they're both positive or both negative. So this is telling us that the particle is accelerating or speeding up. Okay. And that's all that one was asking. So D, can we find the position of the particle when a change in direction occurs? Okay, so a change in direction is saying from the origin, when did it change directions? It's another way of asking about turning points or local mins and local maxes. So we're looking for when the velocity function is equal to 0. Visually, that looks like a position like this, where it was going away from the origin and then back towards the origin. So we have the velocity function from A, so I'm just going to set that equal to 0, and we already solved this. We found that we generated a positive 1. Okay? So when we do that, we can then just look at what is happening. What is the position? So what is the S function when t is 1? Because S just represents our position. So when I plug in a 1 into the position function, I end up getting a negative 1. Okay, this is telling me that the particle is 1 centimeter to the left of the origin when there's a change in direction. Okay, and then we're off to F. So F is saying what's the total distance traveled from T0 to T2. So I want to know, add this up and add this up, the total distance. So what you're going to do is make sure that you're testing from the origin to a turning point or any turning points and then to the final position. So for us, that looks like we're going to be testing what's happening from T0 until T1, which was our first turning point. And then we're going to be looking at what's happening from T1 until T2. Okay, so that basically is telling me I'm looking at what's the position at 1, and I'm going to remove the position at the origin. So it's going to tell us the total distance here. Okay, so the total distance at 1, we actually just found that up here. The position at 1 was negative 1, and the position at 0 we actually found up here, and it was 1. So I'm getting an overall distance of negative 2. And remember, when we're talking about the total distance traveled, the sign doesn't matter. This is just telling us it has traveled 2 centimeters. Okay? And then in this one, we're going to do the position at 2 minus the position at 1. Okay? When I plug 2 in, I get a 3. When I plug 1 in, I get a negative 1. So I'm getting a total distance of 4 between these two. So now I'll just add up 2 and 4. Again, disregard the negative because we're looking at the overall distance traveled. So we can say total distance of 6 centimeters. Okay. And then last up, it says, for what intervals of time is the particle speeding up or speed increasing? So we're looking for acceleration. Speed increasing would be another way of wording acceleration. So we learned up here that we're going to be looking for when the velocity and acceleration have the same signs. So I'm just going to redraw our sign analysis down here. So when we had tested this in A, and we said it was negative and then positive. Okay. And then we had tested the acceleration above 0. And it was all positive. So the region that it would be increasing would be from 1 and above, because they're both positive in that region. So let's write this as a way of describing the domain. So they're both speeding up when the time is an element from 1 to infinity. I'm going to end this video here. If you feel like you'd like another example, I will put it in as a separate video. But good luck. You can try out the problems on page 267. Okay? And then make sure you're looking through the solutions, whether it be mine or the ones in the textbook. And we'll touch base tomorrow.